Our first talk is entitled Telescopes and Observing Instruments, and that's going to be given by Dr. Jane Clark from the Cardiff Astronomical Society. But first of all, just a few words about Jane. Jane is a retired amateur astronomer and has a PhD in physics and an MBA from Warwick University. Jane became interested in both astronomy and photography as a teenager in the 1970s, photography much more seriously. Although as her career progressed and family commitments increased, both interests lapsed. She acquired a telescope in 2006, shortly after completing her MBA, and quickly became hooked on observing. This experience made her realize that astronomy is a lot more fun than business administration. In 2017, she achieved her ambition of having an observatory in her backyard. Jane is a member of Bristol, Cardiff, and Newtown Astronomical Societies, and was a founder member of the West Norfolk Astronomy Society. Jane gives talks on astronomy to astronomical societies, schools, and other societies as diverse as the Cub Scouts, University of the Third Age, and Church Wives groups. So, I'd like to hand over to you, please, Jane, to talk on telescopes and observing instruments. Thank you.
So, the first point I want to make is that in science, observation leads theory, and observation always trumps theory. Sometimes it takes a while to get a consensus about what the observation actually is, but once it's made, if your theory fails to describe or predict that observation, your theory is thrown out. And this is an absolutely key point. When theorists lose contact with observers, as often as not, frankly, they produce codswallop. And I trained as a theoretical physicist and was working in a different university from the people doing the experiments. And that was a formative experience for me. Then when I left university, went into industry and was in the lab with people, either sometimes watching them, sometimes supervising them, sometimes getting my hands dirty doing the experiments. That grounded me a lot more, and that was a revelation to me. And a classic example of a theory that's totally lost contact with observation. You may have heard the term string theory. Well, last I heard, they had reduced it to 10 to the 500 theories. That's a 1 with 500 zeros after it. That means there is a 1 with 27 zeros after it, theories for every second the universe has been in existence. And if that's not rubbish, I don't know what is. Now, visible light. Visible light is light that our eyes can see. And white light, like the color of this background here, can be split into primary colors by a prism. Newton famously did that. And when you go from the red color there all the way down to the violet color there, the wavelength of the light gets shorter. So you can see for all the, it was Newton, I think, who divided the rainbow into 7 colors, but it's a bit arbitrary. And you can see that the wavelength gets, as you start with red and go down there, the wavelength gets ever shorter. And another color could be similarly split. For instance, yellow consists of red and green in primary colors. In reflected colors, of course, yellow and blue makes green, but that's not true of emitted colors. Right, visible light telescopes. They're also called optical telescopes. They do 3 things. The first is that they magnify, so they make faraway things look bigger. They brighten things because the aperture of the telescope is a lot bigger than the pupil of your eye. So they can collect more light than your eye can. And if you put a camera there, the exposure time for your eye is roughly 1/10 of a second. You put a camera in there, you can lengthen that time, which is another way of collecting more light. And the other thing that telescopes can do is sharpen. Good optics can capture more detail. And the bigger the telescope, in principle, the sharper it is, assuming that the telescope is well made, and also assuming, as every observational astronomer knows, that the atmosphere cooperates. if you've got very shimmery air, then it doesn't matter what telescope you've got, you're going to get poor optical quality. And here's pictures of a few different types of telescopes. There's one in space, the Hubble Space Telescope. That's the most famous of over 50 telescopes that have been put in space. These are different types of amateur telescopes. And in this case, this device here is called the mount. And one bit of advice I'd give to anybody who buys a telescope is the place where you spend your money is on the mount. That's more important than the telescope, if anything. Because what the mount will do is it will track. And if your telescope is too heavy for your mount, which always happens with these cheap ones you buy in Argos, then you're going to get a wobbly telescope, which isn't very good. Now, if you want to know how telescopes work, unfortunately, I haven't got time to explain that here. But if you look in my book, there are copies I've donated to both Cardiff and Bristol Astronomical Society libraries. So it is available, and available from all good booksellers as usual. Then there's an explanation in there of how telescopes work. Other light wavelengths. See, there's red to violet, the visible light. And in fact, the light can come in wavelengths, well, any wavelength you like, practically, really. There's, a micron is a millionth of a meter. And the wavelengths of visible light is just under a millionth of a meter. But it can be as long as a kilometer, or as short as a nanometer is a billionth of a meter. That's a 10 billionth of a meter. And what the brown shows is how much of that particular wavelength the Earth's atmosphere lets in. Because, very selfishly, we want to breathe. And very selfishly, we don't want to be fried by all the X-rays and stuff the sun chucks out. So it completely ruins astronomy, but there you go. And so if you want to observe in wavelengths where this number is 100%, like there, or there, you've got to go out above the atmosphere to do it. I think we tend not to observe in that kind of wavelength. I mean, 10 meters is the practical limit of what we observe. And that's aside, there's a new technique now which doesn't use light of any wavelength at all, called gravity wave measurement. A gravity wave is quite different from a wave of light. And we've got gravity wave detectors now. So that's a completely novel way of looking into space. So there we go. Now, radio waves can penetrate the air. That's a bit of a well, duh, because otherwise we wouldn't use those wavelengths to transmit radio broadcasts and television broadcasts. Because if they did go through the atmosphere, there'd be no point. But because there's all that radio noise around, putting a radio telescope in the middle of Bristol is not a great idea because it'll pick up, Radio 3 or whatever. So the big radio telescopes tend to be in very remote parts of the world for that reason, because there's not a lot of other clutter around in those parts. And we can and do observe gamma rays, X-rays. Ultraviolet is this region here, just beyond the violet. We observe that. And infrared is just longer than red. Some of it we can observe from the Earth. I've got a filter for my telescopes, which I can use to try and I'm going to use it tonight actually because it's forecast to be clear, to try and photograph a galaxy using infrared wavelengths around here. See what I can go up to just over a micron. Because there's a particular galaxy where you're supposed to be able to see spiral arms in the infrared, but you can't see them in visible light. So I'm going to try it and see if I can do it. And, it'll either work or I'll fall flat on my face. So that's that. Now, big telescopes have for visible light. For most of the 20th century, the biggest telescopes were 100 inches across, and then, well, during World War II, that kind of time, they built a 200-inch one in California. They were the biggest for a long time, but now the practice is to put them on mountains because they're above as much as possible of the atmosphere, and to put them in places where it doesn't get cloudy. So there are now 4 322-inch telescopes in Chile. That's those 4 there. There's bear in mind that my telescope, which is I've got 2 telescopes. I've got a 3-inch and an 11-inch. An 11-inch, you can go up to 14 inches with amateur telescopes, but not very many people do because they get pretty expensive. And in Britain, they're not much use anyway because all they do is magnify the atmospheric shimmer. So you need those in a kind of place with quiet atmosphere. In Hawaii, there are 2 394-inch telescopes. In the Canary Islands, there's a group of telescopes. The biggest is a 410-inch. And in Chile, there's one, that's the picture of it, that one there. They're building one, which is an absolute monster. And it's the Europeans, who are European Space Agency, of which the UK is a part, building that, and it's going to be a 1,540-inch telescope. So that's more than 100 times the diameter of my biggest telescope. And one of the techniques to improve ground-based telescopes, one's interferometry, and the thing about interferometry is that it allows telescopes to be daisy-chained using electronics, so that if they're a mile apart, you've effectively got the optical performance of a telescope a mile across. In practice with optical ones, they're a few hundred yards apart. And the other technique is adaptive optics. You break one of the mirrors into cells and drive each cell with at least one hydraulic piston. And you measure the air turbulence, which is the jargon term is seeing, and you move the mirror cells about 60 times a second to counteract the turbulence. And that's what you can see in this image here. That's what the image would look like left to itself. You measure the distortion there, and then that's the recovered image after you've subtracted off the distortion. And you can see a lot more in that one than you can in that one. Radio telescopes now, for those very long wavelengths. That's the European Southern Observatory's very large telescope. And it's an array of telescopes, and they use interferometry to daisy chain them up to make effectively one diameter. And some of these telescopes are actually on railway tracks so that you can move them apart. Now, one of the biggest advantages, if you do that, because the wavelength's a million times that of visible light, in principle, to get an image, you need a telescope a million times as big. And that's why they have them far apart. And the early ones were basically just listening devices. But one of the biggest advantages of radio astronomy is that molecules, which are joint up atoms, like, water is H2O, 2 hydrogens and 1 oxygen. Well, the vibrations of the atoms within that molecule vibrate at radio frequencies, so you can pick them up and detect them with radio telescopes. Now, that's an image there, which I took, showing a visible image of a group of 3 galaxies. And I've superimposed on it a radio image taken with this telescope here to resolve the atomic hydrogen. And you can see, if you count atomic hydrogen, the galaxy is now a lot bigger than if you just look at visible light, and the spirals continue outwards. And there's a line there from there to there. So that's a smoking gun evidence that that small galaxy has collided with this big one. There's a more complex picture of hydrogen joining that. So it's not quite so obvious that this one's collided with that, but it looks as though it probably has. So that's the kind of thing you could do with radio frequencies. And of course, if you want to look for chemicals that are relevant to life in space, again, because you need infrared and radio frequencies to detect the vibrations in the molecules. X-rays. Now that's just a drawing. It's an artist's impression. Nobody's ever seen that, but it shows a black hole which is in orbit around this star here, and it's so powerful gravitationally that it's sucking stuff off this star, and it whirls it around there, and then due to a phenomenon which is the gravitational analog of magnetism, it's throwing matter out that way. That emits X-rays. So with an X-ray telescope, you can detect it. Neutron stars also emit X-rays when they're paired in binaries like that. And galaxies emit X-rays as well. Now, you need a completely different type of optics. You basically reflect the X-rays from the object there. Here's a picture of an X-ray telescope. The X-rays come in there and they get focused by these parabolic and hyperbolic mirrors to a point there like that. Now, the other tool that people use for observational astronomy, besides telescopes, is spectroscopy. And spectroscopy is simply, it's as revolutionary as the telescope. Newton, as I said, was the first one to record that light splits into colors. Herschel, the guy who discovered the planet Uranus, discovered that not all light is visible because he had a prism there to split the light into its spectrum, and he moved his thermometer along to see which was the hottest, because obviously everybody knows that sunlight feels warm on your hands. And what he discovered was that there was some warmth out here where he couldn't see anything. So that's how infrared, with a wavelength longer than that of red, was discovered. And the next discovery was this guy Wollaston discovered that there are gaps in the spectrum of the sun. It's not just continuously red to violet. There are gaps there as well. And this idea was developed by Fraunhofer. And so you could use spectra as chemical tools. From the spectra, you could deduce chemical information because these lines of either missing light or light like that, if you're emitting. You see, there's hydrogen, helium, neon, sodium, and mercury, which you can easily make lamps to emit those in a laboratory. You can see they've all got different spectral lines. So that gives you a tool to work out what's emitting it. So we know, for example, that stars are mostly hydrogen. That's how we know what's in the atmospheres of different planets. And it's also how we know, together with infrared spectroscopy to look for molecules, is how we know what's in nebulae. And in the infrared and in radio frequencies, you get the same idea that there are spectral lines. They're just not visible. Spectra can be used as thermal tools. The Victorians gradually discovered this, and the reason why it was solved in the early 1900s by these two guys. You might have heard of Einstein. Stars are classified by color and therefore by temperature. This was mostly done at Harvard University. They had observatories in the northern and southern hemisphere and used spectroscopes to collect tons and tons of photographs of stars. And then the women weren't allowed to use telescopes, but they were employed to go through the data. And most stars are, if you know the surface temperature of the star, you know everything about it from the theory of stellar evolution. And that's quite a remarkable fact that one parameter is enough to know everything else about the star if you can calculate it. So you get a peak. Temperature in Kelvin is degrees centigrade plus 273 degrees and a bit. And when you're out in the thousands, that 273 is neither here nor there. So that's 7,000 centigrade, 6,000, 5,333, 4,000, and 3,000. And the peak is at different wavelengths. So that's how you can tell the temperature of the star. At the surface, anyway. The next revolution from spectroscopy is that movement, that point there is moving to the right. That's the idea. oops, went back one. That point there is moving to the right. And the wavelengths get compressed there, so they're made more violet. Or on this side, it's moving away from you, and so they get made more red. That's called red shifted or blue shifted in the jargon. So there's the spectral lines when it's not moving. There they are when it's red shifted, and there you can see that that broad line has moved. Now, what can you use that for? You could use it to observe orbits of binary stars. You can measure the orbits of stars around galaxies, and you can measure the expansion of the universe. So that is a really useful technique. Now, one thing to say about spectroscopy, this guy is Francois Cochard. He's French. I have met him. He's the founder of a company called Chaliac Instruments. And if you know your stars, you'll know that Chaliac is the name of a star. That's where he got it from. And I heard him say in so many words that amateur astronomers never use spectrographs on telescopes, and professionals never use telescopes without spectrographs. And that is a device that he designed, which is a spectrograph for use on an amateur telescope. And I've got one. And one of my next projects, I'm writing a book on galaxies at the moment. When I've done that, I'm going to go back and learn to use my spectrograph. So, if you are a beginner, what telescope should I buy? Well, that depends what you want to do. Do you want to do visual observing and perhaps sketching? Do you want to do photography? And if so, photography requires much better mounts for your telescope because your eye can kind of allow for your telescope juddering around a bit. A photograph cannot. So you need to keep your telescope absolutely blinking still. And it needs to be strong enough to do it when there's a slight breeze. Now, my advice to everybody is start small and trade up. That's certainly what I've done over the years. I mean, there's a vibrant second-hand market, and you know we can point you to. There's a specialist website, UK Astro Buy Sell, for buying and selling astronomy kit, but you find it on eBay and Facebook and all those places. And a good part of the reason why there's a vibrant second-hand market is because people start big and bite off more than they can chew. Because trust me, it takes a while to learn to use the telescope properly. Don't ignore binoculars to start with. You can do a lot with binoculars. Do a lot of research. Talk to people who've got telescopes. There are several types of telescope on the market. And the reason for that is because none of them's good at everything. So talk to owners. And I mean, I've built my observatory over 18 years. And the last time I traded up was my 11-inch, which I traded up in the last 3 weeks. And my previous 11-inch, which was a less sophisticated one, I'm going to put for sale on UK Astro Buy Sell as soon as I've cleaned it up and taken photographs of it. Another thing, well, you wouldn't be here if you hadn't done this, is join a club and use their kit to begin with to get a feel for what's going on. And it is completely key that astronomy is not an instant gratification hobby. After 18 years, I'm still learning how to take pictures. So that's my story. Thank you very much.
Well, thank you, Jane, for an excellent talk. Great introduction there to telescopes and observing instruments. Sorry we've taken you away from a clear night to do your own observing, so really do appreciate your time in giving us that introduction. So some virtual applause for Jane, please. Thanks very much. We've got time for some questions at the end of the session, so we'll come back to them after our next talk. So our second talk is now on the agenda, and that's on the title of Space Probes, and that will be given by Dr. John Henn from the Bristol Astronomical Society. So before I hand over to John, a few words to introduce John. When John was a boy, he always wanted to build flying saucers and launch them from Peru, and he was inspired by the radio series Journey into Space. In 1971, as a member of the Hawker-Siddeley Dynamics team, John watched Europa 2 being launched from Kourou in French Guiana, the north coast of South America. The first stage was Blue Streak, which worked perfectly. However, the Italians were proud that their satellite was still sending signals when it hit the ocean. John has a degree in physics from Warwick and a PhD in magnetic suspension from Sussex. He has worked in Filton on various space and defence projects and later produced online learning software. John says about himself, being a dreamer, I like to try the impossible. So I got involved in 1984 with trying to restore the 70-mile long, very derelict Wiltshire and Berkshire Canal. And John is still very much involved in that today. John was brought back to astronomy by evening classes with Dr. Rodney Hillier and joined the Bristol Astronomical Society a few years ago, becoming a committee member, and in his own words, has been causing problems ever since. End of quote. So on that topic, John, over to you now, please, to talk about space probes. Thank you.
So yes, I also worked in space on one or two satellite projects years ago when I was young. Yeah, at the beginning of the dawn of the space age. That was amazing. Right. So what are space probes? Space probes are unmanned. They collect data from our solar system and beyond. They study various phenomena and send findings back to Earth. So effectively, these probes act as our distant explorers. So what is a space probe? The anatomy of a space probe. It's got an attitude and orbit control system, which allows instruments to be pointed to the right targets. It allows, if they've got solar panels, it allows those to be orientated towards the sun. And it very importantly allows the communication aerials to point towards the Earth. As part of this attitude and orbit control system, there's a propulsion units. Sometimes the propulsion units to move the total satellite forward or accelerated or decelerated, and also to change the attitude of the probe. So that's the propulsion and thrust system. Then you've got the electric power, and that's in this image is from solar panels. And these are got a high and low gain antenna, and these are used to transmit data from the satellite back to Earth and to transmit instructions from Earth to the satellite. And then, of course, there's a science payload. This will depend on what the mission is. So, but it will often usually has a camera or several cameras and a magnetometer and a spectrograph of various sorts. So this is a Mariner 10, and it's got the solar panels. And this is an image of the Cassini spacecraft. And there's much more detail. And a couple of things you will immediately notice, there's no solar panels. And the reason being is that it's got thermoelectric generators to provide the power for the spacecraft. The thing is, as you go further out into the solar system, the light arriving from the sun decreases rapidly. And so when you get as far as Saturn and Jupiter, or Jupiter and Saturn, there's very much less radiation coming to power any solar panels. And you'll also notice here is the Huygens Titan probe. So quite a few spacecraft, particularly those going to Mars, have had landers of various types. So the next thing you need to know is, how do you get the probe to where you want the probe to go, especially if you're sending the probe to the outer solar system. As we see from this, this is the Earth's orbit, and as you go further away, a probe will decelerate, and as you go towards the sun, the probe accelerates. And the key thing is that the launch vehicle will not have enough velocity to send probes to the outer solar system. So we use a technique called gravity assist. The first part of this gravitational assist is to send the probe to a planet, which will give it a gravity assist. So it's not intuitive. We want to send the probe out to the outer part of the solar system, but the first stage is to send it inwards towards the sun, and in this case, we're sending it towards Venus. And this is a transfer orbit. So this is the first stage is a transfer orbit from the Earth, and it uses minimum fuel. So once this transfer orbit has found a planet, you then get this gravitational assist. So this is the Cassini probe trajectory. So it's launched in 97. And then the first encounter with Venus was the 26th of April, 1998. That accelerated the probe, and it then had a second encounter with Venus in June 1999, and it followed by in August 1999, and by this time it's traveling pretty fast. It flew past Earth, which added a gravitational assist, and then it flew past Jupiter, get another gravitational assist before arriving in the Saturn orbit. So you have to send it past planets to accelerate. So what you do is you send the probe very close to a planet, and as it approaches the planet, it accelerates, and as it goes away from the planet, it decelerates. But if you send the probe in the same direction as the planet, it gains velocity. If you actually send the probe in a direction opposite to the orbital rotation of the planet, it decreases velocity. So basically, that's the gravitational assist. So we're going through this very quickly. But so the next thing to do is say, where have we sent probes? So we've sent probes towards the sun. This is the NASA's Parker Solar Probe. So this flew through the corona of the sun, came within 4 million miles or 6 million kilometers of the sun. And because it's so close, it has to have a heat shield to protect the electronics of the spacecraft. So we've sent them to the sun, looking at the solar wind. We've sent them to comets. This is the Rosetta, launched in 2004. And it was the first probe to follow the comet's orbit. And it was also the first probe to land a probe on the body of a comet. And the lander, Philae, bounced twice. So it landed 3 times, touched down 3 times on the comet. And the bouncing was because it was such a low gravity. And unfortunately, the third touchdown, the probe ended up in shadow. So the solar panels didn't work. So we've sent probes to comets, and we've sent probes to asteroids. So this is Osiris Apex probe, which was designed to get a sample from asteroid Bennu and return it to the US of A, which it did last year. It landed in Arizona, I believe, and that was very successful. And this is a close-up picture of the probe picking up material from the comet. So we've also, the various other missions have produced material from asteroids. and the DART project even crashed into an asteroid trying to move successfully moved its trajectory. This is the deep impact type stuff. So we now look at the bigger targets like the planets. So we're going from inner planets to the outer planets. So Mariner 10 passed Mercury in 1974. And then you had the Messenger probe, which orbited from 2011 to 2015. And that was terminated by crashing into the surface. And then on its way at the moment is Bepi-Colombo. This is a picture taken by Bepi-Colombo in 2021 as it's passed Mercury on a gravity assist. And the Bepi-Colombo mission is joint between the European Space Agency and the Japanese Space Agency. So this is image of Mercury, a mosaic taken by Mariner 10, showing a very pitted surface. And this is a close-up taken by Messenger during its orbiting period. I think the original aim was to take about 1,000 photographs. They ended up by, I believe, taking something like 200,000 photographs of Mercury. So the scientists are still analyzing what they found. So next planet out is Venus, and there have been more than 46, including a lot of gravity assist flybys. So the Russians explored Venus initially. The Soviet Union and the United States have soft landed probes on the surface. The most recent lander was part of the Russian Vega 2 mission in 1985. So in some respects, it's a lot easier to land a probe on Venus than it is on Mars because the atmospheric pressure is so much higher. As well as landing probes on the surface of Venus, we've had several orbiters, notably Magellan, 1990 to 94, and it used synthetic aperture radar to effectively photograph the surface of Venus. By understanding the topography, they then could look at the internal dynamics of the planet, and that's produced some incredible photographs. And then the Venus Express, a bit later, investigated the atmosphere of Venus. So the early probes, as I said, were Russian. Venera 7 landed in 1970 and it sent signals from the surface for 23 minutes. And I think this is an amazing picture of the Russian spacecraft. So this is Venera 13 in the background, and this is the lander. And what I'm just struck by is how chunky they look. So they had some big rockets to send these probes to Venus. So this is a picture taken by Venera 13 in 1982. So it's the probe lasted 2 hours on the surface of Venus, and the reason being it's come to the high temperature and pressure. The temperature is something like 460 centigrade, and the pressure is 95 bar on average. When you think about the atmospheric pressure on the surface of Earth is 1 bar. So that's why the probes don't last very long. So from the orbiter, that's the picture you see with visible light. That's the picture obtained using the radar system. And this is just some of the pictures taken from the orbiter. So this is Maxwell Mons, which is 11 kilometers above the mean surface of Venus. These are small cone volcanoes. There are apparently an enormous number of those. This is an anemone volcano because of the way that the lava flows. These are pancake volcanoes, which are fairly flat domes from 10 to 100 kilometers in diameter. And these are rills, which are caused by lava flows, and they're hundreds of kilometers long. These two are impact craters, and this crater here is particularly interesting because you've got an extensive outflow, which extends approximately 600 kilometers. So it's a very liquid lava, because that's one of the reasons the surface of Venus is so hot. So from a very hot planet, we go to a much colder planet, Mars. Over 50 missions, dominated by the US survey. ESA come in as well, but is now joined by other countries, including China. So the first probe to investigate Mars was Mariner 4, and that cruised by on 14th of July 1965. And the first pictures from Mariner 4 showed craters, and this sort of killed the myth that there might be canals on Mars and vegetation. It showed that Mars was more like the moon than a viable, livable planet. The Viking landers were the first craft to land on Mars in 1976. There were two identical landers with orbital spacecrafts. Then followed various rovers. The first rover was Sojourn, which they call a micro rover. It was 25 pounds in weight, and that's Sojourn. This was followed by much larger Spirits and Opportunities in January 2004. And you will notice that these are using solar panels. And solar panels are a little bit of a problematic on Mars because you have a lot of dust, and the dust actually coats the solar panels and stops the rovers working. Curiosity landed in 2012, and that was powered by a nuclear radioisotope. And Perseverance, which landed in 2021, is very similar to Curiosity, a little bit more modern. This is a false color image taken by Opportunity, enhanced. And the reason it was enhanced is so you could follow the tracks of the rover. So this is an incredible picture taken the summer of 2014. And if you've got time, it's well worth going into NASA's gallery of pictures, because there's some absolutely incredible pictures of Mars. So this is a selfie taken by Perseverance, and the main thing here is Ingenuity, the helicopter. And that's an amazing piece of technology. So the helicopter is designed to fly in the very rarefied Martian atmosphere. So the atmospheric pressure on Mars is about 6 millibars. Atmospheric pressure on Earth is about 1,000 millibars. So this helicopter was proof of concept, designed to do 5 flights over 30 days. It smashed that, doing 72 flights over 3 years. And in the end, it was helping Perseverance by plotting the routes that Perseverance should go. And unfortunately, it crash landed and broke one of the rotors. But it's paved the way for other flying objects on planets. So this is the landing places of the landers and the rovers. There's Perseverance, Opportunity, Curiosity. So the thing is, they landed on the interface between the Southern Highlands and the Northern Plain. So that's some of the landing places. The orbiters have taken some incredible pictures. This is Olympus Mons, which is the largest volcano in the solar system. Something like 25 miles high and 250 miles across. This is the Butterfly crater, which is a sort of a glancing impact, is a low angled meteorite came in there. This is Valles Marineris, which is the Grand Canyon of Mars, which makes the Grand Canyon of the USA very like a pimple. So this is 4,000 kilometers long, up to 600 kilometers wide, and 10 kilometers deep. So it's a huge scar on the face of Mars. This is Eridania Basin, which 3.7 billion years ago was filled with water. We reckon was filled with water, and there's hydrothermal vents underneath it. Very similar to places on Earth at that same time, which were the dawn of life. So it is quite possible that life formed on Mars 3.7 billion years ago, same time as life started forming on Earth. This is a dust devil, 60 kilometers high, 60 meters across. These are recurrent slope linea or lineae, which extend during the summer. So it is believed that these could be water. This is just sand and a dune. So it's just another image of the sand is caused by the atmospheric wind. So that's quite interesting. And the Mars orbiters have been going for 20 years and have taken some absolutely fantastic pictures. So we next go to the Voyager probes launched in 1977. Both Voyager spacecraft passed near to Jupiter and Saturn for gravity assists. This is a Voyager 1 image showing a volcanic eruption on Jupiter's moon Io, which was quite a shock to everybody at the time. Then Voyager 1 on the 14th of February, Valentine's Day, 1990, turned the cameras round, took a picture of the Earth, the pale blue dot. So everything that we know of is on that pale blue dot. So Voyager 2 went past Uranus and Neptune, taking pictures of those two planets, before Voyager 1 and Voyager 2 are now headed off into interstellar space. They passed the termination shock, the heliopause. So there is a great big bubble caused by the solar radiation from the sun. And so the solar system's in this huge bubble, and both probes have gone through the bubble. So the bubble is about 19 light hours away from the sun. These are stars that will get that the probes will have to travel 19 light years. So we don't have to worry about that at the moment. Jupiter probes, 8 have visited the system. Galileo orbited the Jupiter system. While it was orbiting, it sent a probe into Jupiter's atmosphere to investigate, and it discovered Ganymede had its own magnetic field and a subterranean ocean. Juno, the other thing is it was orbited in 95, Galileo, and terminated in 2003. Juno launched 2011. Couple of things to note. Unlike other probes in the outer solar system, it's actually got solar panels, and it was sent over the poles of Jupiter to investigate the poles. And on its way is JUICE, Jupiter's Icy Moons probe, and that will explore Europa, Callisto, and Ganymede. And it'll be the first probe to actually orbit a moon, and it will eventually orbit Ganymede. So these are just a false image of the Juno, taken by the Juno probe. And this is another picture taken by the Juno probe. And it just shows that Jupiter actually has got some faint rings, and that shows that it's false color so that you can show the aurora better. And I think that's the big red spot. So normally that's red. So the Galilean moons are very interesting on the Jovian system. You got Io, the volcanic moon. You got Europa, the water moon. You got Ganymede, the biggest moon in the solar system, and Callisto, which is the third biggest moon in the solar system. Believe that Ganymede has this ocean underneath it. But certainly Europa has an ocean. It's encased in a thick crust of ice covered with globe-spanning liquid water. And in fact, there's more liquid water on Europa than there is on Earth, which is sometimes you think it's a bit amazing. So the next planet out is Saturn. And it's the Cassini-Huygens probe, launched in 97. So Cassini spent 13 years cruising the system and produced some incredible pictures. It took many pictures of the rings of Saturn, and it took pictures and close-ups of the various moons. And this is Enceladus, another watery world, which is believed to have a nice surface and a liquid water ocean underneath. And these geysers emanate from Enceladus. And in fact, the Cassini probe was sent through this late on in its mission. And it discovered this was water vapor and hydrocarbons, possible life on Enceladus. So the next moon is Titan, which is the second biggest moon in the solar system. And it's only one with a substantial atmosphere. So it's only place besides Earth known to have liquids in the form of rivers, lakes, and seas on its surface.
2 minutes, please, John.
Right, surface is minus 180 degrees, liquid methane and ethane rather than water. So you saw the probes landing on the surface of Titan. Unfortunately, the spacecraft had no more than 3 hours of battery life, most of which was used during the descent. Lastly, but not least, is the New Horizons probe. So it launched in 2006, flew past Pluto in 2015. And it was incredible. It showed a planet. People thought it'd be a dead planet, but it wasn't. It had mountains, 10,000-foot mountains made of water ice. Some of these mountains could well have been cryogenic volcanoes. And then the Sputnik Planum, which was this area here, didn't have any craters, so it's very new. And it's probably nitrogen ice, and there's a heat source from the center of the planet, which is recovering the surface. And then the final object, New Horizon, went past Arakoth in January 2019, and apparently the science community has sent back to the drawing board to understand how platissimals, building blocks of planets, form. So that's incredible. Thanks for watching. That's the comet, that's Jupiter, and that's Saturn. There we go. Thanks, folks.
Well, great. Thank you, John. Thank you for an excellent overview of space probes over the years. And I must say, incredible images there you had in your talk of the planets and the moons. I particularly wonder at the surface of Venus. It's a fantastic image.
Well, it's amazing that, and I think I would recommend everybody to go and have a look and find some more images, because there's a huge amount out there.
Sure. Great. Thanks very much. Okay, so great talk, and virtual applause for John, please, for putting all that together. Thank you very much. So we've just had one question come in this evening because of, I think probably both talks answered all the questions people may have had. But we've had one question come in for Jane, and it's really in relation to the best place to look for second-hand astronomy equipment and telescopes. Any comments on that, please?
There we go, UK Astronomy Buy and Sell.
So you don't have a 9 1/4 inch SCT to sell then, Jane?
I have an 11-inch.
11, I know you've got an 11-inch now. I thought you had a 9-inch before that, didn't you?
No, I had an 11-inch before, but I had the ordinary one. Now I've got the enhanced one called the Edge HD.
Great. Okay. Right, well, thanks for that. I think
most of those photographs I've put on Facebook were taken with the 11-inch. It's a fabulous telescope.
Yeah, absolutely. And I must say to everybody who's attending tonight, if you want to look at some of the amazing photographs that Jane takes, and also other members too, look on our Facebook page, where there's regular images that are posted there. You have to be a member of the society of the Bristol Astronomical Society to look at that Facebook page.
But I put them on the Cardiff one as well.
About to say, they'll be equivalent for Cardiff and for Bath as well. So have a look on those sites and you'll see those great images.
And if you can't get on the Cardiff one either because you're in Bath, the Newtown Astronomy Society's one, I believe, is public. So you can get on that. And it's not Newtown Astronomical Society, it's Newtown Astronomy Society.
Okay. Thanks, Jay. So that, I think, is the end of our questions for today. Just one reminder, in the chat session this evening, we had some comments that the recording for the first session on Google wasn't working properly. Well, thanks to Fiona for resetting that. So that first session should work now if you want to catch up on the first lesson. If any of them are not working, then just drop us a line and we'll sort them out. But thanks for sorting that, Fiona. So thanks again to our speakers, Jane and John, for 2 excellent talks. Thank you for everybody for dialing in this evening and for the questions that have been raised. I think we've responded to them all, but if any come up later, then please put them on an email or on a future chat box and we'll respond to them. So it just remains for me to say that our 5th session will be held on Tuesday the 12th of March over Zoom, again 7:15 for 7:30 start. And the theme of that 5th session will be the history of astronomy. And an invitation for that will be sent out soon. So look forward to seeing you then on the 12th of March, and goodbye to everybody for now. Goodbye.